Hi everyone, this is Mrs. J, and today we're going to be reviewing constant and linear functions. But first, please pause the video and give this warm-up a try. All right, go ahead and check your work here. So we're essentially just making a table of values using the equations given. So for the first function, f of x equals 2, you'll notice that there's no x in the equation on the right side. So that means it doesn't matter what the x value is, the y value will always be 2. And you end up with a horizontal line at y equals 2. So this is what a constant function looks like. And then here we have f of x equals x, which is the parent function for our linear function family. So essentially whatever x is, the output y will be the same, and you get a straight line equation that looks like this. Okay, so we're going to start off by doing a quick recap of constant functions, which we just graphed in the warm-up. So constant functions are actually a type of linear function. They're a linear function that has a slope of 0. So that means that they will always end up with a horizontal line graph, and it's just going to be at whatever the c value is. So y equals c will just be a horizontal line at that c value. So for these, our domain is always going to be all real numbers. You can see our graph stretches to the left and right infinitely. And the range is just going to be one value, which is c. So we could put that in little braces to show that. That's the only y value that exists. And c can represent any real constant, so any real non-variable number. All right, let's try this one really quick together. This is the only constant function we're going to be graphing today. It says f of x equals -3. So again, I know it's constant because I don't see that x in the equation. So I just find y equals -3, and I do a horizontal line through that point. So it's all the times when my y value is -3. And that's it. So just remember, if you don't see an x in the equation, it's not a typo. It just means it's a horizontal line through that y value. All right, so now let's talk about linear functions. So in the warm-up, we made the parent function for our linear function family, which is also this, y equals x, or f of x equals x. So linear functions are functions that have a constant slope. And remember, slope is rise over run. So it means that they're increasing or maybe decreasing at a constant rate, which means their graphs will always make straight lines. So for our parent function, you'll see that the domain and range are both all real numbers. And you'll also see that for the parent function, the y-intercept and also the x-intercept is at the origin. So it goes through the point 0, 0. And if you look at the rise over run, rise meaning vertical distance and run meaning horizontal distance, which would give us our slope, the slope is going to be +1. So that's what our parent function looks like. Now, of course, that can change depending on if we change the equation, but that's kind of our starting point for linear functions. So there are two different forms of linear functions that we work with. First is called slope-intercept form. Hopefully this looks familiar. Y equals mx plus b. For this form, m represents the slope of our function, and b is the y-intercept. So this form is really ideal for graphing. When we graph, if we can start with the y-intercept and then we simply follow the slope to the next consecutive point, we can make our graph pretty quickly and easily. Now this next form is called point-slope form. So it's y minus y1 equals m times x minus x1. This is going to be a really important form of our linear function. M also represents the slope in this one. And then you can see that we have this x sub 1, y sub 1, so x1, y1. And that just represents any coordinate on your graph. So this form is really nice for modeling because you still need the slope like you need for slope-intercept form, but this one any coordinate will allow you to make the equation. For slope-intercept form, you have to know the y-intercept, which is a very specific coordinate, but here, any point on your graph will work. And then, of course, we do need to sometimes know how to find our own slope. Sometimes it'll be given for us, or we can see it in the graph. Sometimes we can't. So to find the slope of a linear equation, you do need 2 points, x1, y1, and x2, y2. But it's simply going to be y2 minus y1 over x2 minus x1. So this gives us, we call this the rise over run. That was another common way of describing what slope is. All right, let's see if we can graph these 4 equations together. So this first one, f of x equals x minus 3. So I'm going to start, I always list out the slope and the y-intercept. So here, m, which is the slope, is always the coefficient of x. So in this case, m is 1. And sometimes it's nice to write it as a fraction. So I'm going to write it as 1 over 1, so I know what the rise and the run are. And then this b value, including the negative, is going to be our y-intercept, and that b value is negative 3. So we always start at the y-intercept, and then I follow my slope, which tells me to go up 1, right 1. And I'm just going to follow that pattern going to the right. And then I could do the opposite of that. If I'm going backwards, it's down 1, left 1, down 1, left 1. And that can give me a few additional coordinates. And you can see when I connect the dots, it makes that straight line. Don't forget to put the arrows at the end. All right, let's try this one. For this one, I can see that our slope is negative 1 over 2. The coefficient of x, including the negative, and our b value in this case is just 0 because I don't see anything added or subtracted at the end. So my y-intercept is at the origin. And when our slope is negative, that tells us to go down 1 and then right 2. So I'm going to go down 1, right 2, down 1, right 2. Or I can do that in the opposite direction and go up and left. And then you connect your dots, and you add your arrows, and you're good to go. All right, so now let's look at this equation. Here you can see that this equation is not in slope-intercept form. So the first thing I'm going to do is rewrite it in that form. So first you can start by adding 8 to both sides. So our goal is to isolate the y value. And then to get rid of this 2, we're going to divide both sides of our equation by 2. When we do that, make sure we're dividing both terms on the right side. Every single term needs to be divided by 2. So we have y equals negative x plus 4. So from here, it's much easier for us to graph. We can see that our slope is negative 1. And if it helps you to write it as negative 1 over 1, that's totally fine. And we can see that our y-intercept is 4. So I'm going to start with the y-intercept at 4, and then the negative slope tells me to go down 1, right 1, down 1, right 1. Anytime your slope is negative, your graph should be decreasing, meaning it's going down if you read your graph from left to right. And this last one here, I'm going to rewrite this in slope-intercept form before we graph. I'm going to add 3x to both sides to isolate the y value, and then I'm ready to graph. My slope is 3, or you could write it as 3 over 1. My y-intercept is positive 1. So start with the y-intercept. We need a starting place, and then we could follow our slope, telling us to go up 3, right 1, or down 3, left 1. And then connect your dots to make that straight line. So remember, when we're graphing a linear function, being in slope-intercept form is really the ideal form for us to graph. All right, go ahead and pause the video and give these 2 a try on your own. All right, go ahead and check. So here you can see I rewrote the first equation in slope-intercept form by subtracting 2x from both sides. So my y-intercept is 1 and my slope is negative 2. So I go down 2, right 1. For the second one, it is in slope-intercept form. Our y-intercept is simply 0, and our slope is 4/3, which means from 0, I go up 4, right 3 to plot my next point. All right, next thing we're going to talk about is how to find an x and y intercept and then use those to graph our functions. It's a different way of graphing. So to find an x-intercept, that's when it crosses the x-axis, so it must be when y is 0. So we set y equal to 0. And to find a y-intercept, we simply set x equal to 0. So if you're able to find an x and a y-intercept, you can actually graph your line. All you need to graph a linear function is 2 points, because if you connect them, it will make the straight line that is your graph. So this is one way that you can graph linear equations. Again, it depends on the form of the graph, and it depends on personal preference as well. So here we're going to find the x and y intercepts of this graph. I'm not going to rewrite it in slope-intercept form this time. So let's start by finding the x-intercept. And again, to do this, we set y equal to 0. So I'm going to say 2x plus 3 times 0 equals 6. So 2x equals 6, which means x equals 3. That's my x-intercept. And I'm going to plot that point. It's where my graph crosses the x-axis. Now, let's find the y-intercept. So to find the y-intercept, we set x equal to 0. So for this, we say 2 times 0 plus 3y equals 6. So 3y equals 6, which means that y equals 2. So that's our y-intercept. So it's where our graph crosses the y-axis. So once you have 2 coordinates on your graph, again, you can actually connect the dots and just graph your line from there. So especially with the x and the y-intercepts, those are really useful points to know. So this is a really great way to graph a linear equation that's in this form. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. Your x-intercept should be -4 right here, and your y-intercept should be +2. All right, so now we're going to practice creating linear equations. So we'll be given different pieces of information about the graph, and then we're going to have to make the equation. Here it does say we're going to write our final answer in slope-intercept form, but most of the time for these, we are going to use that point-slope form to model. So this is the form that's most commonly used to create an equation. So for this first one, we are given the slope of our function, which is m, and we're given a point, -4, 3. So since we have the slope and a point, we have everything we need to use this point-slope form. So remember, this is our m value, and this is x1, and this is y1. So all I'm going to do is substitute. We have y minus y1, which is 3, equals m, which is 1/2, times x minus -4, which is x1. So notice I have the minus sign from the equation, and then the -4 comes from the x value of my coordinate. So now I just need to distribute and solve for y to write my final answer in slope-intercept form. So we have y minus 3 equals 1/2 times x plus 4. And again, I'm going to distribute the 1/2 here. So y minus 3 equals 1/2 x plus 2. And then I'm just going to add 3 to both sides to get y equals 1/2 x plus 5. And there you go. So although we typically like to write our final answer in slope-intercept form, again, when we're making an equation, I'd like you guys using point-slope form to do so. All right, let's look at this next example. Here, we want to make an equation that goes through these 2 points. So you notice that I have a coordinate, actually I have 2 coordinates, so I could use either one, but I don't have the slope. So the first thing we're going to need to do is find the slope of our line using our slope formula, which is right here. And I'll call this x1, y1, and I'll call this x2, y2. So we're simply going to substitute to find our slope first. So we have -1 minus -4 over 2 minus 1. So our slope is -1 plus 4 over 2 minus 1, which is 1. So our slope is +3. Now once you have the slope, you can actually pick either point, and then we're going to use our point slope form, which is right up here, to make our graph. I'll just use this first coordinate, but either one will give you a correct answer. So we have y minus y1, which is -4, equals m, which we found to be 3, times x minus x1, which is 1. So I just substituted 3 and then x1 and y1 here. So it gives us y plus 4 equals 3x minus 3. I distributed the 3 to my binomial. Then I'm just going to subtract 4 from both sides. So y equals 3x minus 7. And just to show you, if we use this other coordinate here, we do y minus -1 equals 3 times x minus 2. It gives us y plus 1 equals 3x minus 6. So y equals 3x minus 7. So if we rewrite it in slope-intercept form, you'll see that we get the same exact answer. So it doesn't matter which coordinate you use. As long as it's a point on the graph, it will get you to the right answer. All right, last, we're going to create a linear equation from a set of values. This is a table of values, like a t-chart. So first thing we need to check is that this actually comes from a linear equation. So for that, we're going to look for a constant change of x and a constant change of y. So what I mean by that is, what do I need to do to get from -5 to -1? Well, here I add 4. And from -1 to 3, I add 4. 3 to 7, I add 4. And 7 to 11, I add 4. So there's a constant change of x, but for a linear equation, we also need a constant change in y. So 4 to 2, we subtract 2. 2 to 0, we subtract 2, subtract 2, and subtract 2. So because there's this constant change in y and a constant change of x, that means that this has a constant slope, which makes it linear. So once I know that it's linear, I can then start to create the equation. So first, let's define the slope. So here, we actually already have the change in y over change in x. So you can use our slope formula, or we could go just straight to our rise over run. We could say -2 over 4, which is -1/2. And then from here, you can pick any coordinate you want from this table to make our equation. I'm going to pick this coordinate because it has a 0 in it, but again, you can pick whatever coordinate you want. So I'm going to pick 3, 0, which is going to be x1, y1. And then again, I'm going to plug it into my point slope form. So y minus y1 equals m times x minus x1. So y equals -1/2 x plus 3/2. And again, you could have used any coordinate, any xy coordinate from that table, and you would end up with the same exact answer. So here, this is kind of 3 different scenarios that we were given, and each time we were able to create the linear equation for our function using that point slope form. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So for part A, I used point slope form because we were given a slope and a point. You should get negative 2x plus 5 as your equation. For part B, first you need to find the slope using the slope formula. So y2 minus y1 for x2 minus x1. And you get a slope of negative 3. And then I use this coordinate to make the equation, but you could use either one. You might have also noticed that this is the y-intercept because our x value is 0. So you could actually go straight to slope-intercept form for this problem. And then for part C, you do need to check to make sure that this is a linear equation. So we have a constant change of x and a constant change of y. So it is linear. I'm going to make a note of that. So I did the slope by doing change of y over change of x, so rise over run, it's positive 3, and then I just picked this first point to make the equation in point slope form. I did it with a second coordinate as well, so first I did it with 10, 7, and then I also did it here with 9, 4, just to show you that it doesn't matter which coordinate you use, you will end up with the same answer by the end. All right, so now we're going to start solving linear equations, and then we'll actually move on to a system of linear equations. So this should be pretty quick and easy for us. It should be 100% review. When you're asked to solve for x, you're trying to isolate x, and you do that by using an inverse operation. So here's x. First, I can move the positive 3 by subtracting 3 from both sides. So negative 1/2 x equals negative 9. And then here, this is like saying dividing by 2, so I can do the inverse of that, which would be multiplying both sides, and I'll do by negative 2. And you get x equals 18. So just using our inverse operation. For part B, we do see that before we can start using our inverse operations, we need to distribute, because we have an x trapped inside some parentheses here. So we have 12 plus x equals 5 minus 3x minus 3. So it's negative 3 times x and negative 3 times 1. And then on the right side, I can actually combine like terms. I can combine the constants, 5 and negative 3. So that gives me 2 minus 3x. Now I need to make sure that I get my x terms on the same side. So I'm going to add 3x to both sides. So 12 plus 4x equals 2. And then I could subtract 12 from both sides. So we get 4x equals negative 10. And then I can divide both sides by 4. So x equals negative 10 over 4, which of course we will always simplify. If you divide the numerator and denominator by 2, we get negative 5 over 2 as our solution. All right, go ahead and pause the video and give these two a try on your own. Okay, go ahead and check your work here. You can subtract 3 from both sides, then divide by negative 4. Make sure you simplify to get your final answer. Then for part B, you need to distribute first, then move your x's to the same side. So I subtracted 5x from both sides and then finished solving to get x equals 17. All right, so the last thing we're going to review today is how to solve a system of equations. So that's where we're actually going to be solving for two variables, for both x and y. And to solve for two variables, we need two equations. So essentially what's happening is we're given two linear equations and we're really trying to find the point of intersection, where they cross. Now you can solve a system graphically. You can physically graph them and look for the point of intersection. However, this only works nicely when they intersect at nice numbers. But that's essentially what you're solving for, that point of intersection. So with two linear equations, they can cross one time, but it's also possible for them to never cross. Right? If you have the same slope with different y-intercepts, your lines will never cross. So in that case, the system has no solution. Now, there is a third case with these types of systems. If you end up with actually the same line with two different equations. So essentially, like when you graph it, it becomes the same line. They have the same y-intercept and the same slope. We call that infinite solutions. It doesn't mean that everything is your answer. It just means that there's an infinite number of times that the lines are intersecting because they're physically on top of each other. So we will be solving our systems of equations algebraically. So there's a substitution method where we essentially isolate one variable in the equation and then substitute it into the other to solve. And then we'll have to do another round of substitution. So sometimes the substitution method's the easiest thing to do, and then sometimes we'll use what's called the elimination method, where we line up the variables and the constants vertically, and then we want to make opposite coefficients for one variable. So we would like to see maybe positive 5x and negative 5x, or negative 2y and positive 2y. So when we add vertically, it eliminates one variable. So that's why we call it the elimination method. Then once we have one variable solved for, we could substitute to solve for the other. So we'll do a quick review of both methods here. All right, let's try this one together using the substitution method. So I'm using the substitution method because I see that one of my variables is already isolated. I have y equals 2x minus 4, which means in the other equation where I see this y, I can replace it with 2x minus 4. So I'm going to do that here. So 3y plus 3x plus 2x minus 4 equals 1. So when I do that substitution, now this equation, instead of having two different variables, only has one. So I can solve for x. I'm going to combine like terms first. I'm going to add 4 to both sides and divide both sides by 5. So I get x equals 1. From here, we're going to substitute x equals 1. And we can do this into either of the original equations. So I'm going to substitute it into the second one. So we get y equals 2 times 1 minus 4. Y equals 2 minus 4. Y is negative 2. So for a system of equations, we write our answer as an ordered pair. So we'll do parentheses 1 comma negative 2. Because remember, what we're really finding is the point of intersection between the two lines. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So this one I noticed that the top equation already isolated x. So x equals 3y minus 9. So I can substitute this x with 3 minus 9, and then I have a single variable linear equation. I can solve for y. I substitute into the first equation to solve for x. So my answer is 3, 4. All right, let's try one using the elimination method. So remember, our goal here is to create opposite coefficients for one of the variables. And it doesn't matter which one, it just depends what looks easier to you. So I see that I have negative 2x and positive 3x. So I know that I could turn them into negative 6x and positive 6x by multiplying my equations. I could also eliminate the y's by turning one into positive 30y and negative 30y, but I think it'll be easier for us to make the x's opposite. So, and again, if I have a 2 and a 3, the least common multiple is 6. So I'm going to multiply the top equation by positive 3 on both sides. And I'm going to multiply the bottom equation by positive 2 on both sides. Make sure you're doing the same thing to both sides of your equation. So that gives me negative 6x minus 18y equals 72. And then I have positive 6x minus 10y equals 40. And now that I have opposite coefficients, I'm simply going to add vertically down my columns. So you'll see that when I do that, we have negative 6x plus 6x, so the x's eliminate. So that leaves me with negative 28y equals 112. And then if we finish solving by dividing both sides by negative 28, we get y equals negative 4. So once you've solved for one variable, you're going to substitute that into either of the original equations. Maybe I'll substitute that into the second equation. So 3x minus 5 times negative 4 for y equals 20. So 3x plus 20 equals 20. 3x equals 0, so x equals 0. So my last step is to simply write my answer as an ordered pair, 0, negative 4. All right, let's try another one together. So here I could eliminate my x's by making it negative 12x and positive 12x. Could also eliminate my y's by making it positive 20y, negative 20y. Let's say this time my goal is to eliminate my y's. So I'm going to multiply my top equation by 2 on both sides. So we have negative 12x plus 20y equals 2, and then positive 12x minus 20y equals negative 2. So when I add vertically, you'll see this becomes 0, and this also becomes 0. So we're left with 0 equals, well, then 2 plus negative 2 is 0. So when your variables disappear, but you're left with a true statement like this, where it says 0 equals 0, for a case like this, it means that we have infinite solutions. So if you look at the equations, they actually are just the same equation, but with multiplied by a different multiple. So if I multiplied my top equation by negative 2, I would actually end up with the same exact equation as my second equation. So when you essentially have the same equation, just in a slightly different form, again, we have infinite solutions. It doesn't mean your answer is all real numbers. It just means you have an infinite number of solutions. So this is what it would look like when you're solving it algebraically. All right, we're going to try one more together. So again, I can eliminate my x's by doing negative 8x, positive 8x, or my y's by doing positive 10y, negative 10y. Let me try to eliminate my x's. So if this is negative 8x, I'd like this to be positive 8x. So I'm going to multiply this by negative 2 on both sides. I'm going to rewrite my top equation. And that gives me positive 8x minus 10y equals negative 26. So when I add vertically, on the left side of my equation, I end up with 0. But on the right side, I end up with negative 5. So here we have another case where both of my variables disappear, but I'm left with an untrue statement. 0 is not equal to negative 5. So if you ever have a case like this, it means that there is no solution to our system, and that will happen sometimes. So again, if you get something like 0 equals 0, it means infinite solutions. If you get 0 equals a different number, it means no solution. All right, here's the last few tries, so please pause the video and give it a shot. All right, go ahead and check your work. So here I noticed that it's probably easier for us to eliminate the y's. So if this is positive 2y, we would like this to be negative 2y. So I multiplied my top equation by negative 2 and lined it up with my bottom equation. The y's disappeared and it left me with just x, so I was able to solve for x. And then I substituted that into my first equation and I was able to solve for y. All right, that's all for today's video. Thank you so much for watching.